Just പറയാൻ പറ്റുമോ? ഓക്കെ, കഴിഞ്ഞ ക്ലാസ്സിൽ നമ്മൾ ഡിസ്കസ് ചെയ്തത് ഷോർട്ടസ്റ്റ് പാത്ത് അൽഗോരിതംസ് ആണ്. ഓക്കെ, Dijkstra's algorithm we discussed. Okay, we discussed the Dijkstra's algorithm, and so this is the first step. This is initialization step. Okay, then these constitute the initialization step. Okay, this is the initialization step. Then there is a while loop, and there is a queue also there. Okay, while the queue not empty, we will extract minimum from the queue, then we'll add it to the S. Okay, add it to S. Then for each vertex v belongs to g dot adjacent of u, we will perform relax. Okay, so what is relax? This is the relax function. Okay, so basically Dijkstra's algorithm is used for finding the shortest path from a source. Okay, this is called a single source shortest path. Okay, it is used to find the distance from a single source to all other vertices. Okay, for example, if you consider this one, this is the final state. So from S to T, the minimum distance or shortest distance is 8. Okay, similarly S to X, it will be 9. Okay, this is the shortest path. Okay, so what will be the path from S to X? Shortest path will be 5, 3, 1, so 9. Okay, so from S to X, the shortest path is 9, which is automatically found by the Dijkstra's algorithm. Okay, so this is called any problems? Okay. So this is single source shortest path. Okay, from a source it will find the shortest path to all other vertices. Okay, that is why it's called a single source shortest path. Single source shortest path distance. So similarly, what will be 7? 7 will be the distance from S to Z, shortest path distance from S to Z. Okay, which will be 5 plus 2. Okay, this will be the path. Okay, similarly, this is the final figure. Okay, anyway, in the previous day I given an assignment. Try to do that. Okay, using this algorithm. Okay, this is the algorithm. Okay, so in this I skipped one topic. I think initialize single source. This. Okay, basically this is actually the code of that. Okay, it is very simple step. We want to initialize all vertex distance to infinity. Okay, you can note here what is initialize single source g comma s. It is a function which initializes the vertexes. Vertexes distance v dot d. Okay, so in this single shortest path distance problems, here instead of key we are using d, distance. Okay, v dot d is equal to infinity, v dot pi is equal to nil, and the start vertex is its distance is initialized to 0. S dot D is equal to 0. Okay. This is about this part. Okay. In the previous day I didn't cover that. Okay, this is that part. Then we will initialize this also. So these all constitute the initialization step. Then while q not equal to empty, we will extract the minimum, then add it to S. Then for each vertex, V belongs to G dot add adjacent of U will perform relax. So what is relax? This is the code for relax. Okay, if V dot D greater than U dot D plus W of UV, V dot D is equal to U dot, V dot D is updated in this way. Okay, this part. Okay, this part and this part is same. Okay, so then V dot pi is equal to U, its parent. Okay, so this is a relax function. And next, so this Dijkstra's algorithm cannot handle the negative weight. Okay, if there are negative weights, then it may not give the exact solution. Okay, so we need another algorithm to handle the negative weight. Okay, that is called Bellman-Ford algorithm. Okay, Bellman-Ford algorithm. Okay, now we want to discuss Bellman-Ford algorithm. Okay, it's also similar to the shortest path Dijkstra's algorithm. We can discuss that. Okay, so okay, please give attendance. Akash Rajiv, Akash, Abhinand, Akash absent ഇടുന്നുണ്ട്. Abhinand, Abhinav, okay, Adarsh V, Adarsh absent. Adarsh 1 minute on attendance. Okay, Adarsh, Advaid, Adarsh, Akash absent. Okay, Adarsh present. Advaid, Ajmal, Akhil Sipur, Advaid. Okay, Anaka, Anjali Anugraha, Adinanil Adulpike Devika, Anjali Anugraha, Adinanil Adulpike, Adin Adul absent. Okay, Adin Adul absent. Devika, Dilna, Masna, Jasna, Devika, Dilna, Masna, Jasna. Okay, Karthik, Kirtana, Muhammad Sinan, Karthik, Kirtana, Muhammad Sinan. Okay, Muhammad Ijaz, Nafa, Neha, Muhammad Ijaz, Nafa, Neha, Neha. Okay, Nidin Babu, Pranave, Pranavsi, Raisa, Nidin Babu, Pranave, Pranavsi, Raisa, Raisa Khalid, Rasana, Riswin, Roshan, Sahalabi, Rasana, Riswin, okay, Roshan present. Roshan, okay. Roshan TP, okay. Sahalabi, okay. Sahalayan, Sangeet, Sarang, Sharun. Sahalabi, Sahalayan, okay. Okay, Sangeet, Sarang, Sharun. Okay. Sangeet, Sarang, Sharun. Sarang absent. Okay, Sarang present. Sangeet, Sarang, Sharun. Shraddha, Vishnu, Vinod, Vaishnavi. Shraddha, Vishnu, Vinod, Vaishnavi. Okay. Baby Srishma, Anjida Rameshan, Shirona. Baby Srishma, Anjida Rameshan. Anjida absent. Anjida Rameshan, Shirona. Shirona absent. Okay. Absent is Anjida, Shirona. Then Advaid എപ്പോഴും വന്നതാണോ? ആകാശ് പ്രസന്റ് ആണോ? ഓക്കെ, നേഹ പ്രസന്റ്. ആകാശ് ഓക്കെ, അഭിനന്ദ് ഓക്കെ. ആദർശ് പ്രസന്റ് ആണോ ഇപ്പോഴേ? ആദർശ് ഓക്കെ. അദ്വൈത് പ്രസന്റ് അല്ലേ? അദ്വൈത് Okay. 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 Now we want to discuss the Bellman-Ford algorithm. Okay. So what is Bellman-Ford algorithm? So Bellman-Ford algorithm, we want to discuss it. Okay. So it is also a shortest path finding algorithm. Okay. So the Bellman-Ford algorithm solves the single source shortest path problem. Okay. Single source shortest path problem in the general case in which edge weight may be negative. Okay. This is one of the property of Bellman-Ford algorithm. That is, it can handle the edge weight with the graphs having negative edge weight. Okay. So next property is Bellman-Ford algorithm returns a Boolean value indicating whether or not there is a negative weight cycle that is reachable from the source. Okay. So this is very important. What is the use? Okay. So the Bellman-Ford algorithm returns. The Bellman-Ford algorithm returns a Boolean value indicating whether or not there is a negative cycle that is reachable from the source. If there is such a cycle, the algorithm indicates that no solution exists. Okay. So if there is a negative cycle exists, then the algorithm should indicate that no solution exists. Okay. So if there is no such cycle, the algorithm produces the shortest path and their weights correctly. Okay. So this is about the Bellman-Ford algorithm. If there is a negative edge cycle, it will detect the negative edge cycle. If there is a negative edge cycle, then it will say that there will be no solution. Okay. Else, if there is no negative edge, it will correctly find the shortest path from a single source to all other vertices. Okay. So this is about the Bellman-Ford algorithm. Okay. Now we want to discuss Bellman-Ford algorithm and Bellman-Ford algorithm and algorithm. Okay. So this is almost similar to our discussed stress algorithm. Okay. So in the first part is the initialization part. Okay. Initialize single source G comma S. So first we want to initialize the graph, vertices in the graph. So this is the corresponding code. Okay. For each vertex, V belongs to G dot V. Okay. Just read it. Okay. You can read it. Okay. For each vertex, V belongs to G dot V. We want to initialize V dot D is equal to infinity and V dot pi is equal to nil. Okay. Then S dot D. What is S? S is the start vertex. Okay. Then we want to initialize the start vertex distance value to 0. Okay. So note that there is no pi value for S because there will be no predecessor for the start vertex. So S dot D only we want to consider. It will be initialized to 0. Okay. So this is about the initialization step. Okay. So next what we will do after initialization, we want to do 2 to 4 steps. Okay. Okay. 2, 3, 4. Okay. That is this is for I equal to 1 to G dot V minus 1. What is its meaning? for I equal to 1 to mod g dot v minus 1 means mod g dot v is the number of vertices in the graph. Okay, minus 1 because we want to exclude the start vertex. So we want to repeat this loop for I equal to 1 to mod g dot v minus 1. Okay, so I hope you got the idea why, what its meaning. G dot v is basically the number of vertices. Okay, number of vertices. Okay, number of vertices. Okay, it is very difficult to present using this tool. Number of vertices. Okay, number of vertices. So minus 1. What is why we are minus 1? Because we are excluding the start vertex. Okay, that is minus 1. So mod g dot v minus 1. We want to repeat this for loop for I equal to 1 to mod g dot minus 1. Then inside that another loop is there. Okay, that is for each edge uv belongs to g dot e. So g dot e is the total number of edges, all the edges in the graph. Okay, so for each edge uv, we want to take each edge one time and do the relax function. Okay, so this is the meaning of this term. Okay, so its meaning is this: we want to take each edge in the graph. We want to take each edge in the graph and do relax function on it. Okay, so what is relax function? In the previous class we discussed what is relax function. So this is relax function. Okay, so what is relax function doing? So I told u is one vertex and v is another vertex. Then the distance between u and v is 2, here 2. Then if we apply relax function, then what will happen? What will happen? Just note it. Okay, this is the distance. Okay, so we will update the distance of this one. Okay, u and v is the neighbor of u. Okay, v is the neighbor of u. If we apply the relax function, then what will happen is that it will update the distance of its neighbor v. Okay, so the condition should be this: if v dot d greater than u dot d plus w of uv. Okay, so what is v dot d? V dot d is, we can check here. For example, here it will check the condition like this. Okay. It will check in this way. 9 v dot d 9 greater than u dot d plus u dot. What is u dot d? U is this. It's a distance 5. U dot d is 5 plus 5 plus this is distance between u and v, w of uv. Okay, w of uv. So it is 2. Okay, 5 plus 2, which is 7. So 9 greater than 7. Okay, this is true. So what will happen? V dot d is updated to, this is basically 7. This is 7 here. It is 7. So v dot d is updated to 7. Okay, v dot d is updated to 7. This is what a relax function is doing. Okay, so for each edge we want to do the relaxation. Okay, for each edge we want to do the relaxation. Okay, so this same concept we used in Dutch-Custer's algorithm also. Okay, we are applying the same concept, relaxation, in Dutch-Custer's algorithm also. Okay, so it will be easy to study for you. So this is relax function doing. So in this 2, 3, 4 steps, for I equal to 1 to mod g dot v minus 1, we want to do these things. Okay, so we will relax each edge. Okay, we will relax each edge in the graph for I equal to 1 to mod g dot v minus 1. Okay. Next, 5, 6, 7. This is step 5, 6, 7. What is the need of this step? What is the use of this step? What is the use of this step? For each edge, u, v belongs to g dot e. If v dot d greater than u dot d plus w u v. Okay. If v dot d greater than u dot d plus w u v, we want to return false. Okay. Basically, this step is used to find what? What is the use of Bellman-Ford algorithm? It is used to find the, if there are negative edges. Okay. If there are negative cycles in the graph, Bellman-Ford algorithm will return that. Okay. It will find automatically. Okay. So in order to check whether any negative cycle exists, we are using this code. Okay. This code. Okay. If there is no negative cycle, it will return true. It will return true. If there is negative cycle, it will return false. If there is negative cycle, it will return true. Okay. So this is about the algorithm. Okay. So we discussed this. Then discuss this also. Then we are going to the example. Okay. So as usual, we will start from where here. Here you can note that there is no separate priority queue. In the Dutch-Custer's algorithm, we used a queue. Okay, we used a queue, but here in the Bellman-Ford algorithm, there is no queue coming. Okay, so okay, so now we are going to discuss the working of this algorithm. Okay, so basically we will start from this is a graph, and you can note here in the figure A, just I am initializing the graph. Okay, so each vertex in the graph distance is initialized to infinity. You can note here infinity, 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 and this is 0. This is the start vertex. So it is initialized to 0, and okay. Then you can note here negative weighted edges are here. Okay, -2, -3, -4, etc. Okay, you can note here. Then what we want to do? We want to take each edge. Okay, so this is the start vertex, and this is the start vertex. Okay, so what we want to do? This is the start vertex S. Okay. Then we want to take an edge. Okay, you can go to the algorithm. For each edge, UV belongs to. For initially, we will set I equal to 1. Okay, 1 less than, how many vertices are there? 1, 2, 3, 4, and 5. Okay, so mod g dot v minus 1. How many vertices are there? 1, 2, 3, 4, 5. So mod g dot v minus 1 minus 1 is equal to 4. Okay, we want to repeat the for loop 4 times. Okay, mod g dot v minus 1 equal to 4. So initially I is equal to 1, 1 less than 4. So what we will do, we will enter this. Next, we will start from here. Okay, we will take an edge. Okay, we will take an edge in the graph, then we will apply relax. Okay, so basically what will happen, note here, okay, so we want to take an edge from S. Okay, this is an edge from S, this is an edge. Then what we will do, we will apply relax. What is relax function meaning? We will update the distance of t. Okay, distance of t. We will update, we will find d. Sorry, we will find the distance of t. Okay, so this is an edge, and so now this is S and this is t. Then the distance t is updated. Okay, the distance t is updated based on which rule? Our relaxation function. This is the relaxation function. V dot d greater than, initially you can note here 6, not 6. Basically initially it's infinity. Infinity greater than 6 plus 0. So it is updated to 6. We are updating 6. Updated t to 6. Then what we will do? We will take another edge. We can go to the algorithm. What is algorithm saying is that for each edge uv belongs to g dot v, 0 d, we want to apply relax. Okay, so initially I is equal to 1. In that case, we taken this. Okay, this edge we taken. This edge we taken. Next, what we will do? Another edge we will take. Okay, and updated this to 6. Okay, next we will consider this edge. Okay, and update the distance to 7. Okay, next we take this edge and update this distance. Okay, so next what we will do, we will take, you can note here, we are taking another edge. Okay, this edge we will take and update the distance this to, update the distance this is 2. Okay, next what we will do, next we will take this edge. For each edge we want to update the, we want to do the relaxation. Okay, so that's why we are doing in this way. Initially we start taken this one, then this one, then this one, then this one. Okay, then this one. Okay, or you can think in this way, after this also taken. Okay, then these distances are updated for 2. Okay, next what we will do, we will take this edge. Okay, this edge we will take. Here you can note here this distance is updated. Okay, we taken this edge. This is a negative edge. So based on that we will update this distance. T also updated. Okay, T updated. Similarly, what we will do, so after doing this, we will get a graph like this. Okay, you can note here we are taking this edge. Okay, this edge we will take and update the distance here. Okay, so we consider 4 edges now. How many edges? We considered all edges. Okay, so we consider this edge, this 1, 2, 3, 4, and 5. 5 edges we considered. Now this is the situation after considering the 5 edges. Okay, so after considering the 5 edges, it will be like this. Okay, it will be like this. Okay, so now we reached the figure E. Okay, figure E. That is, we are just executing this algorithm for each edge UV belongs to D. We want to relax. We want to apply relaxation. Okay. After applying the relaxation, 1, 2, 3, 4, 4 times. This is a loop. Okay. We are executing this code. I equal to 1 time. Okay. So this will be basically, we want to repeat these steps how many times? 4 times. We want to do the for loop 4 times. I equal to 1 to mod g dot b 4. So this is the case of I is equal to 1. Then when I is equal to 1, this will be the case. Similarly, we want to do for I is equal to 2, 3, and I equal to till I equal to 4. Then we will get a final graph. On that, we want to execute this code. Okay. We want to check whether there is a negative cycle or not. Okay. Then we can discuss in the next class. In the text, they given the case when I is equal to 1 only. One iteration only they given. Okay. One iteration only given because we want to consider a lot of cases. So this is one iteration of the for loop. This loop. Okay. This is one iteration of the third step for each edge. Sorry, second step. This case. Then we want to update I is equal to 2. Then again we want to do the relaxation. Then we want to update I equal to 3. Then we want to do the relaxation of each edge. We want to do relaxation. Then up to I is equal to 4, we want to do the relaxation. Then we want to check whether there is any negative cycles or not. So I think here only first case is given. Okay. So in the next class we can discuss the remaining portions. Okay. Okay. So this is about the Bellman-Ford algorithm, and in the next class we can discuss the full details. Okay. So this is Bellman-Ford algorithm. So what is Bellman-Ford algorithm means? It can handle the negative edge cycles. Okay. Also, it will find the shortest path from a single source to all other vertices. Okay. So this is the structure of the algorithm, and this code is for finding the edge weight, shortest distance. This code is for finding the shortest distance this code is used for finding the shortest distance. Then this code is for finding the negative edge cycle. Here we want to repeat this for loop for I equal to 1 to mod g dot v minus 1. Okay. Then for each I value, I want to do the relaxation. Okay. So how it will correctly work, we can discuss in the next class. Okay, so this is the initialization step, and this is the relaxation step, and this is the working. I can discuss that in the next class.